Right, so sort of main sort of new topic tonight then, integration by parts. More complex procedure, so carries more marks than the exam. Okay. Just like the others though, with practice it becomes more and more straightforward until in the end it's pretty well as straightforward as some of the other textbooks we look at. It's all about practice at the end of the day. And it comes from the idea of the product rule for differentiation, which if you remember is to differentiate two functions multiplied together, it's the first function multiplied by the differential of the first plus the second multiplied by the differential of the first. If you play around with that, we can use the same sort of rule. Actually, this is the same sort of rule as the product rule, but for integration. And if you look at the example, we've got two functions, 3x and e to the 2x. X appears twice, two functions multiplied together. So we've got to use a rule to do this, and the rule is integration by parts. What it's saying is, if I want to integrate u dv, it equals uv minus the integral of v du. That's what that's saying. So how do we put this into words, and how do we apply it? Well, what we do is we say, okay, product rule is telling me the integral of u times dv, and actually this is often sort of put left out, but it means dv by dx, equals uv minus the integral of v times du by dx. So in other words, if I let one part of my integral be u, so I'm going to let 3x be u, and the other part of the integral be dv, so I'm going to let e to the 2x be dv, then this example looks like the left-hand side of the rule, the integral of u dv. So if I let u equal 3x and dv equal e to the 2x, that is the integral on the left-hand side, isn't it? U equals 3x and dv equals e to the 2x, which I'm going to write down in a minute.
But dv.
Yeah. What it really means is dv by dx, but we don't often put that in. You'll see it written like this: u dv equals uv minus vv. Probably best to do it by example, but I'm going to sort of talk about how it works as I go along, because the hard part of this method is to decide which bit of my integral I've got to do I'm going to call u, and which bit am I going to call dv. I chose to let 3x equal u and e to the 2x be dv. I could have chosen to do it the other way around, but there's a reason why I chose to do it that way. If you look, I'll explain it and then you'll see it work by example. If you look at this, and I'll sort of use my magic pen to highlight it. If you look at this, if I let the u part of this equal, no, I don't like that, let's use the yellow highlighter. If I use u, let u equal this, then what I'm actually turning this integral on this left hand side into is another integral on the right hand side, but in this integral, instead of u, I've got du. In other words, the differential of what I've let u be. And what's the differential of 3x? 3. So if you think about it, I've now got an integral where the one of the x's has disappeared, so I can do the integral. That's how it works. Let me show you by going through this example, and maybe you'll see it. But it does take a little bit of understanding the first time you see it. So I let u equal 3x, but I need du, so I differentiate it. So the bit I call u, I differentiate. What's the differential of 3x? 3. The other bit of the left-hand side integral that we've been asked to do, we've called dv. So dv equals e to the 2x. In other words, the differential of v is 2x, e to the 2x. But if you look at the product, or this rule bar that is of integration by parts, I want to turn an integral that involves dv into one that involves v. So I need the integral of this. So what I do is, okay, I say dv equals e to the 2x. So v equals the integral of e to the 2x. And that's a standard integral. The 2 comes down and goes underneath. So this is a half e to the 2x, or e to the 2x over 2, same thing. Now just pause while you make a note of that. Okay, so let's just recap. What do I do? And the principle, the process rather, is the same every time. I decide to let one bit be u and the other bit be dv. And which bit is which is important and is with practice. So I'm going to let u equal 3x. Why do I let u equal 3x? Because I need to differentiate u, and that means the x is gone. So I let one bit equal u and differentiate that. I let the other bit be dv and I integrate that. So that process is the same every time. I let one bit be u and differentiate it, and the other bit be dv and integrate that. So then I can combine these steps. I can add this up to say that therefore the integral of 3x times e to the 2x with respect to x, our original interval, becomes u, using my law of integration by parts, u, which is 3x, multiplied by v, which I worked out to be a half of e to the 2x, minus the integral of v, which is a half e to the 2x, times du, which is 3. Let's just recap that then, okay? What have I done? My original integral of 3x e to the 2x, I let the 3x be u, so that's this part, the u in here, okay? And then I let e to the 2x be the dv bit. And so now I'm going to replace that integral with this right-hand side, right, Daniel? So, in other words, now this equals u, well, what's u? 3x. So in other words, that's this u bit here, times v, and v was a half e to the 2x, so that's v, minus the integral of v, which is a half e to the 2x, times du, which is 3, and then I'm going to integrate. So that's where the rule comes from. That's the uv minus the v du. So this is the integral of u dv, turns out to be uv minus the integral of v du. So what have we done here? We've changed it into another form. And if you look at this integral now, this integral that we've got to do, no longer have we got another x in there. It's just the integral of a half e to the 2x times 3. And that's a doable integral. That's likewise we've been doing. So we can do that. So carrying on, this equals, and tidying up as we go along, if we look at the first part, 3 times a half becomes 3 over 2, x e to the 2x, minus, I could take the 3 and the half outside the integral, so this is 3 over 2 integral of e to the 2x dx. So now I've got an integral, this right-hand integral here, that I can do. So finally we get this equals 3 over 2 x e to the 2x minus 3 over 2. Now I do this integral, which is again the same as the one we've just done. The 2 comes down and goes underneath, so that's a half e to the 2x. And then now we've nearly finished, we add our c at the end, plus c. And all we've got to do now is a bit of tidying up, because I can factorise this. 3 over 2 can come outside a bracket, and so can the e to the 2x. So finally the integral becomes 3 over 2 e to the 2x into x minus a half plus c. I'd like to just finish this particular example off then just by sort of summarising it a bit and just showing you and highlighting some of the steps. What was the first integral we had to do? So let's put that at the bottom. The integral of 3x e to the 2x with respect to x becomes, now if we write this line again, this line here, then that's the uv minus v du bit. So if we rewrite this line, this equals 3x times a half e to the 2x minus the integral of a half e to the 2x times 3 dx. I've written this line so that we can just underneath write the integral of u dv, so that's the u bit and that's the dv bit, equals uv, that's the u bit and that's the v bit, minus the integral of v du. So that shows you, I hope, exactly how that fits into the rule. So what have I done looking at this? I've turned an integral into u dv. I've let one bit be u and the other bit be dv. And then the bit I've called dv I've integrated to get v, which is a half e to the 2x, and what I've called u I've differentiated to get du, which is just 3. And then I've plugged those numbers into this formula, this method, this integration by parts method, to end up with a solution. And after that, what the whole point of it is that I end up at the end here with an integral that's doable, because x only appears once. So we can do it now. We couldn't do it here because x appeared twice, there and there. Okay? Okay, let's look at another example. So, right, let's apply this rule, integration by parts, to this example. I need to use integration by parts because x appears twice, two functions multiply together. So it's the product rule, but the integral version of it, which is this. First step, decide what I'm going to call u, what am I going to call dv. And the first clue is to think to yourself, whichever bit I call u, if I differentiate it, does x disappear? And if it does, that will work. If I call ux and I differentiate x, it's gone, isn't it? It's just 1. The differential of x is 1. So that's the one to let u. So let u equal x. The bit I've called x, u rather, I need to differentiate it. So du by dx equals 1. So if I've let u equal x, the other bit has got to be the dv bit. So dv has got to be cos x. remember, I leave out what I should put in really is by dx. In other words, x is the variable, but that's not put in the rule because it could be any variable, any letter, so we can leave it out. So if the differential of v is cos x, then v is going to be the integral of cos x. Yeah. If dv equals cos x, v is going to be whatever the integral of cos x, which is sin x, yes. So in other words, v equals sin x. So I'm part way there now. I've decided what I'm going to call u and differentiated it. I've decided what's going to be the v bit and I've integrated that. So now all I've got to do is plug them into the product rule, sorry, the integration by parts rule. So the integral of x cos x, my original integral, equals u, which is x, times v, which is sin x, minus the integral of v, which is sin x, times du, which is 1. And that was the whole point of doing it, so that that x disappeared. So now, what we do is, okay, the first bit is done now, x sin x, minus, now I've got to perform an integral. So, what's the integral of sin x? Minus cos x. No, a minus cos x. Sin x becomes minus cos x. And then finally we try and tidy it. Notice minus a minus gives us a plus. So x sin x plus cos x. And that would be as far as you could go with it. That would be the answer. Again, just so we can see the rule, okay, let's look at, to show the rule, let's look at this again. What did we do? The original integration was, what's the integral of x cos x? Equals, and if we write this line down here, which was the first one we wrote, this one, then that will give us our rule. So, equals x sin x minus the integral of sin x times 1. And so this shows us the rule because we can now say, okay, the integral of u dv equals uv minus the integral of v du. So that's the u bit, that's the dv bit that we assigned at the start, and the integral becomes u times v minus the integral of whatever v is times whatever du is. And at that point we see that it becomes an integral we can do because one of the x's has disappeared. So, we let u equal 3x because when we differentiate the u, that's going to leave just 3, so the x has disappeared, which is good news. So let u equal 3x. Whatever we let u be, that's what we differentiate. Differential of 3x is just 3. So if we let u equal 3x, then dv must be sine 2x. So v is going to be the integral of sine 2x, which is, the 2 comes out and goes underneath, sine becomes minus cos, so it is minus a half cos 2x. So, you know, as you were saying, John, it's all, you know, once you're more familiar with those little steps, then the easier the rest of it gets. and that only just comes with practice. So now our integration, which is the integral of 3x sine 2x with respect to x, becomes u, which is 3x, times v, which is minus a half cos 2x. So put that in a bracket because it's negative, minus the integral of v, which is minus a half cos 2x, times du, which is 3. So hopefully you got that. Now we've just got to do it. Minus a half times 3 is minus 3 over 2 x times cos 2x. So that's that bit tidied up. Minus a half and the 3 can come outside of here, but minus 3 over 2 times minus and minus is plus 3 over 2 integral of cos 2x dx. So I just brought the constant, the 3 over 2 outside. And because it's a minus minus, that gives us a plus. So, okay. And now I perform the integral. What's the integral of cos sine? So, and the sine, the 2 comes out and goes underneath. So finally we get minus 3 over 2x times the cos of 2x plus 3 over 2 times the integral of this, which is a half sine 2x. And then we're going to add the c at the end. We can factorise. 3 over 2 can come outside a bracket. Leaving minus x cos 2x plus a half sine 2x plus c. You don't have to factorise, you could leave it as it is there. If you are going to factorise, though, it's not a good idea to start off with a negative term because you could easily miss that negative sign.
Yeah. So what I was saying about cancelling each other out, is that wrong?
Well, I wasn't quite sure what you meant by cancelling out, so I'll have to come and have a look. A half sine 2x minus x cos 2x plus c is probably how I'd leave that solution. Okay, so I think you can see that it's down to practice, isn't it? So I suggest now, if you have a look at the textbook, there are some more work problems, and next week I'm going to start off looking at 2 in particular. Work problem number 5 and work problem number 6, because not always do we let x equal u. So I'm going to start off with next week by looking in particular at work problems number 5 and 6. So if you wanted to look ahead at those, do so. And then this exercise that follows on. Okay, I don't know what that is. Is it 196 in the new textbook? I think there's a 10 difference or something. Yeah, so you can have a look at some of these. And the solutions, I've done some solutions for the first few already of this one. So you could look at the video.
5 and 6, which is that similar?
Work problems 5 and 6, yeah, there'll be the same work problems in your textbook, just a different page number.